The pH scale is a logarithmic scale. What that means is 1 unit is equal to a tenfold change. Okay, so whenever we talk about the pH changing by 1 unit, so going from pH equals 1 to pH equals 2, what we're seeing is a move from times 10 to the negative first to times 10 to the negative second. So that's a tenfold difference there. Likewise, you see the same thing on the opposite scale. When our pOH goes down, 14 to 13, for instance, you see that exponential change from negative 14 to negative 13. Now, what you need to know about that all is pH of some of our common liquids. Well, we have a range from 1 molar HCl, which gives us a pH of 0, to 1 molar sodium hydroxide, which gives us pH of 14. HCl, strong acid, sodium hydroxide, strong base. Okay, everything in the middle, you're not going to worry too much about, because more times than not, what we are doing is we're hanging out right about there at a pH of 7, a neutral pH. Okay, now the dissociation of weak electrolytes. So here what we have is CH 3COOH plus H2O. Now this one right here, I remember in Mrs. Jones's AP chemistry class, we had to memorize our polyatomic ions, and CH3COOH, man, I don't know, it was just a stickler for me. That's acetic acid. Acetic acid is a weak acid. It has such a cool name, but still it's a weak acid. So by virtue of being a weak acid, it's a weak electrolyte. Weak electrolytes dissociate only partially in water, so we don't have that 100% separation that you do with a strong acid. The extent of the dissociation is determined by the acid dissociation constant, or K sub A. Okay, now we can calculate the pH if our K sub A is known, but we need to do some algebra. Dissociation of weak electrolytes. We've got an example here. So what we're asked to do is, what is the final pH of a solution with 0.1 moles of acetic acid is added to water to a final volume of 1 liter? Okay, so this shows us our formula for acetic acid, and I'll always remember in Mrs. Jones's AP chemistry class my senior year of high school, I was really on top of memorizing my polyatomic ions. But CH3COOH, you could tell me what's the formula for acetic acid, and I'd be like, oh, I think there's a C, and then there's a bunch of other stuff. I really struggled with that one. Now, what we can do is we can assume that our acetic acid, is the only source of hydrogen ions in this mixture. Okay. Now we have our K sub A, which is our acid dissociation constant. Now, what we can do with that is say we know that we're starting with 0.1 mole, specifically 0.1 molar. That's our concentration, our initial concentration of acetic acid. And what is going to happen is that is going to dissociate into, well, this guy right here is going to dissociate into this and this. We have no clue what the concentration of this and this are, but we know that whatever it is, it's coming from the 0.1 molar. So what we're going to do is we're going to set up our calculation where K sub A is equal to X, concentration of our dissociated, times concentration of our protons, divided by, well, our initial concentration of acetic acid minus whatever we lose. And we know that that acetic acid is going to dissociate into the deprotonated form and a proton. So we know that. We're good there. So we've got this set up as X times X divided by 0.1 minus X equals 1.74 times 10 to the negative 5th molar, because 1.74 times 10 to the negative 5th is our K sub A. What we can do with that is do the simple algebra that tells us that X squared, take this right here, this bottom half, multiply that by that guy right there. X squared is equal to 1.74 times 10 to the negative 6th minus 1.74 times 10 to the negative 5th times x. Okay, so now what we want to do is we want to get x on its own side. And so that's going to get us, well, 1.7, add that guy right there. And when we do that, once we've gotten the 1.74 times 10 to the negative 5th x on the other side of the equation, we also recognize that this is a quadratic. And so our quadratic ax squared plus bx plus c equals 0. Well, we need to recognize that for what this is. And so we need to plug it into our quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. Sorry, flashbacks from, I don't know, was it the high school, I think? So you can plug all that info in there, and whenever you do that, you solve for our x value, which is going to be this 0.001310, and plug that in because that is your hydrogen ion concentration right here, and that gives you a pH of 2.883. All right, so there you go for solving a quadratic with the weak electrolyte. Now, dissociation of weak electrolyte, somewhat simplified. This equation is a little bit easier than that because you can go ahead and say that, the amount of hydrogen ions, the concentration, the relative concentration of protons that are dissociated from our acetic acid, because it is a weak acid, we can say that's negligible, in which case we plug it in, and rather than this right here, this 0.1 minus x, we get 0.1. Plug all that into our k sub a, and oh, suddenly this is much easier. X squared is equal to 1.74 times 10 to the negative 6th, which ultimately, there's your x value, there's your pH. Our difference, well, it's not even it's not even really noticeable. This is going to work for sufficiently weak acids and bases. All right. Now, this gives us, this scale right here, this display right here shows us the relationship between pKa and pH. Okay. Now, what I'd like to do is I'd like to draw your attention to this guy right here. That's our acetic acid again. And our pH, if you look at the bottom of this, we've got our pH scale right here. So from 1 to 14. Now we've got our pKa right here. And our pKa is, boom, right there. At that pKa, we've got this dissociation from our fully protonated form of that acetic acid to a deprotonated form of that acetic acid. So pKa is a good measure of acidity, and that's something that's worth recognizing about this, because that's helpful when we're talking about defining different amino acids. Now, buffers are mixtures of weak acids and their anions, also known as conjugate bases. Buffers are going to resist changes in pH. So at a pH that is equal to a pKa, there's a 50-50 mixture of an acid and an anion form of a compound. So we just showed that acetic acid, I'm just going to write that as AA has a pKa of 4.76. So what that means is that this molecule right here, that molecule is going to undergo changes based on an environment, because we know that we can make a solution with a specific pH. So if you make a solution with a pH equal to 4.76, well then that solution's pH is equal to our acetic acid's pKa, which means you've got 50% of that acetic acid that's protonated, 50% that's deprotonated. Okay. Now, buffering capacity of an acid anion system is greatest when our pH is equal to our pKa. Buffers are still functional, but they grow a little bit weaker as you get farther away from the pKa. So acetic acid with a pH of 4 or pKa of 4.76, this is a good buffer at pH, let's say 3.9 or 4.9, but at 5.9, I'm going to do a frowny face because we've gotten too far away from that pKa. So it's lost a little bit of its ability to maintain the pH. Okay, so here's a display of a titration curve, and I'm going to go really far into titration curves when we talk about amino acids, but basically this is a titration curve for acetic acid. We have our pKa at 4.76. So what that means is we have an equal concentration of this protonated form and the deprotonated form. Okay, so in our pH, the solution that we made with a pH, and then we threw a bunch of acetic acid in there, when that pH was 4.76, we had an equal concentration of these two substances. Okay, now as our pH went up, what happened? Well, the concentration of our deprotonated form of acetic acid, well, that's going to go up. What's going to happen to our protonated form's concentration as our pH goes up? Well, the concentration of our protonated form goes down. So this is an important thing to understand, and I would take some extra time to make sure that I know this. You can simplify it as a molecule, molecule is protonated when the pH is less than the pKa. Okay, so what that means is we've got a bunch of hydronium ions floating around in there, and basically enough hydronium ions to populate every single place on a molecule that can be protonated. Now, our molecule is deprotonated when our pH is greater than our pKa. When our pH is equal to our pKa, well, we have an equal concentration of those two different forms. Again, this is something that it's good to feel good about now, but when we get to amino acid structure, we're going to go ham on this. All right. Weak acids have different pKa's. So here's acetic acid, here's phosphoric acid, and here's ammonium. Ammonium has a pKa of about 9.25, phosphoric acid has a pKa of 6.86, and acetic acid has a pKa of 4.76. So not all weak acids are created equal. Now, the way that we can look at this is by using something known as the Henderson-Hasselbalch equation. Hasselbalch. I always forget about that second L right there. Hasselbalch equation. Okay, so the Henderson-Hasselbalch equation, what you guys need to know about it is pH is equal to pKa plus a log, or a ratio basically, of the deprotonated form and the protonated form of your acid. So that's essentially what you need to know about it. Deriving it, you don't really need to worry too much about that. But think about it like this. Going down here, when we have an equal concentration, let's say 5 millimolar of the deprotonated form of something compared to 5 millimolar of the protonated form of something, they're equal. Okay, so if you have log of 5 over log of 5 over 5, that's the same as log of 1. Log of 1 is equal to 0. So that gives you pH is equal to pKa. Now, this question right here gives us an example of a Henderson-Hasselbalch equation, or calculation. A buffer is comprised of 0.1 molar acetic acid. I apologize. acetic acid has a pKa of 4.76 and 0.05 molar sodium acetate. Okay, so that's sodium acetate, that's our conjugate base, that's our anion form of that, or our deprotonated form of it. That proton's been replaced by a sodium ion. The question is, what is the final pH of our buffer? So what we need to do, or all that we need to do, and I kind of showed my hand right here, is we need to take 0.05 divided by 0.1. That gives me 0.5. And whenever you take the log of that, that's going to be log of 0.5. That is equal to negative 0.301. Okay, so 4.76 minus 0.301, that final pH is equal to 4.45. Okay, so that's basically all that it is to a Henderson-Hasselbalch equation question. You just have to know the concentrations, and you have to be able to identify those different species. So this right here, that's our protonated form of our acid, and our sodium acetate is our deprotonated form of our acid. And I know a lot of people who have gotten thrown off by this sort of question because they see sodium acetate and they think, well, what the heck, where's that sodium acetate coming from? Look back at that formula and say it's acetate, it's CH3COO. That's just like my deprotonated form of acetic acid. The only thing is we're using a sodium ion in place of our hydrogen or our proton. Okay. Biological buffer systems. Maintenance of intracellular pH is vital to all cells. Enzyme catalyzed reactions have an optimal pH, which we're going to get into in the future. Solubility of polar molecules depends on hydrogen bond donors and acceptors. Equilibrium between CO2 gas and carbonic acid or carbonate depends on pH. So, respiration depends on the pH. Buffer systems in vivo are mainly based on phosphate concentration in the millimolar range, bicarbonate and histidine. So those three players, phosphate, bicarbonate, and histidine, are all going to play or have an impact on a in vivo buffered system. Okay, so the last thing is buffered systems in vitro are generally based on sulfonic acids of cyclic amines. Okay, so heaps, pipes, and CHES. These are common. So think about these as common experimental buffers. So think about this slide as basically, hey, it's important to have the pH or maintenance and maintaining a pH is very important. Okay, well, the next group of things is here's how it's done in vivo, and then the last is here's how it's done in a laboratory setting. Now, what this shows you is a little bit of a preview, and I kind of appreciate that, but I want you guys to appreciate this. What this is showing is we've got a whole lot going on here, and I think it's pretty darn cool. We've got this blue area, which is your protein. Now we've got ASP235, ASN232, MET204, ARG151. What is all this? Well, those are the individual amino acids, and what this is showing you is all of the different bonds that are taking place, specifically hydrogen bonds that are taking place between a substrate molecule right here and water molecules and all of the different amino acids within this protein. So if you remove water from this reaction, well, you wouldn't have all of the hydrogen bond networks established, in which case you wouldn't have this reaction. I believe this is going to be a sugar. Yeah, we've got something happening with a sugar here, but this is just, to me, it's a pretty cool representation of showing how water itself is very important and hydrogen bonding is very important to establish all of these different networks. Well, that wraps up chapter 2. I hope this was helpful, and thank you very much.